Okay, we're going to continue on here. Very last chapter of the season here, which is equilibrium, and chapter 17. And in this chapter, we're going to talk about equilibrium. We're going to talk a little bit about rates of reactions, talk about Le Chatelier's principle. Why we're doing this, I don't know, but we will, I suppose. You will again see this, when you take 1B eventually, I suppose. But we'll talk about what's going on here in this chapter. So the first thing we're going to talk about is really about rates and sort of what is important in terms of a reaction to sort of take place, right? So as we've talked about in some of these other chapters, in order for a reaction to take place, we do need to have some type of collision to occur. And this collision does need to actually happen in sort of the right location. It needs to sort of occur in the active site. Not all collisions will actually lead to products being formed. So you can have things sort of hit each other and it will not actually make a product. What also needs to happen is usually the correct amount of energy needs to be there as well. So there's sort of two components for really reactants to sort of convert themselves over into products. They do need some type of collision to occur in the correct location, and those collisions do need to basically happen with the right amount of energy, bless you, to allow those reactant molecules basically to get all the way over to the product side. Now, when we talk about a rate, and especially when we talk about a rate of a chemical reaction, that usually is something, has units of something like molarity per second, kind of the change in the concentration. And again, when you see the little bracket, that usually means concentration. And that usually means, in most cases, molarity, which is our moles per liter. Can be other things, but usually that over a change in time. And that's usually the rate that we look at. Now, there are factors that affect that, but as a reaction takes place, one thing to remember, as we talked about with a chemical reaction or a chemical equation, the only thing that really changes is bonds. So we basically just break bonds and make bonds. And that is basically all electrons. So really electrons are kind of the only thing involved in a chemical reaction. We don't touch anything in the nucleus, so we don't touch any protons, we don't touch any neutrons. And as you hopefully remember, it is the protons that are really important in terms of elements, right? So if we don't touch anything in the nucleus where we have our protons, that is why we have to balance equations, right? And that's because if we started with 4 carbons, we should end with 4 carbons on the other side of the arrow. The only difference is they may be in some different compounds. So because we really don't do anything in a normal chemical sort of reaction with anything in the nucleus, it's all about bonds and electrons, we have that conservation of elements. And again, that's why we have to actually balance our equations. So as a reminder, this is sort of what happens. We have a couple of these reactant molecules coming together. They're going to collide here, hopefully with the right amount of energy. The result of that is it's going to, as is proceeding from reactants to products, it's going to start working on kind of breaking the old bonds and really at the same time kind of work on making some of those new bonds that are necessary. And we will get to this point where we have this sort of intermediate that sort of occurs between sort of the reactants and the products, where we have something that has sort of partially broken bonds and some partially made bonds at the same time. And then relatively quickly after that, usually, it will kind of drop down to the other side where your products are, and you'll make your new sort of substances. There are a couple of things that are really important in terms of the rate of a chemical reaction. And rates, by the way, when we talk about rates in chemistry, that is the area of study that's known as kinetics, which you will also do in 1B, by the way, when you get there. And kinetics tells us how fast or slow a reaction basically takes place. So two really important sort of aspects of that is concentration of the reactants. So the idea here is if you have a really high concentration of your reactants, so for example, you have a really high molarity or something like, 4 molar, 12 molar, whatever it may be, a pretty good concentration, or even really 1 molar, a good amount of products, right? When we talk about molarity, again, that is technically moles of solute over liters of solution. A reminder that it is the solute molecules that are actually what is reacting when you do a sort of chemical reaction. It's actually those solute molecules that are basically coming together and reacting. So the idea here is if you have a really good amount of concentration of your reactants, if we just draw our reactant molecules as circles here, there is a fairly good chance that those guys do not have to go find each other. It's not going to take them a really long time to find other reactant molecules to react with. And what that's going to do is increase the rate of the reaction because, frankly, they don't have to go very far to find somebody to react with, right? Now, the opposite is true. Obviously, if you have a really low concentration of reactants, so you have a really low concentration, they're kind of sparse, if you will, then. You got kind of sparse guys floating around. It's going to take much longer for these guys to kind of find each other. The result of that is your rate of your reaction is going to probably slow down. So that availability of things that are to come together to react definitely increases the rate of the reaction. The other major thing that definitely helps increase the rate of reaction is temperature. And temperature will help the reaction speed up typically when you increase the temperature. And when you increase the temperature, typically you'll see an increase in the rate. For example, if you increase the temperature about 10 degrees Celsius for a lot of reactions, that is enough to basically double the rate. So that reaction will occur twice as fast by just simply raising the temperature. The idea behind that is as you raise the temperature, frankly, everybody's got a lot more energy. So that's also going to have things starting to move around more. That's going to allow more contact between reactant molecules. And because it's at a higher temperature and they have more energy, when they actually do come in contact with one another, they probably will have sufficient amount of energy for that reaction actually to take place. So it'll actually help along the way. And you can even think about it, for example, if you're dealing with something like gas molecules. You got some gas molecules, you increase the temperature, they're going to be flying around a lot faster. So they're going to definitely probably come in contact with each other a lot more often, a lot more frequent, and that is all going to increase the rate of the reaction in that particular case. Any questions on that there? Obviously, as well, the opposite is true. If you were to lower the temperature, if you took all your test tubes, for example, you're going to do your reactions in and you threw them all on ice and you really lowered the temperature, you're removing a lot of energy from that reaction. The result of that is everybody's going to kind of slow down. And when they do come in contact with each other, you're probably going to have less reactant molecules that have enough energy really to get over to the product side. And that ultimately is going to really kind of slow down the rate of your reaction. So concentration, again, increases that rate just from availability of everybody able to react with one another. Temperature, again, as we've just been talking about, has definitely an ability to increase the rate. You may remember this diagram or a diagram like this. This is an energy diagram. And we have our reactants here and our products. And a reminder that there is that hill that the reactants has to climb to get to the other side, and that is the activation energy. And that activation energy, as it says there, and as we talked about, I think in chapter 10, is the minimum amount of energy that's required for a reaction to take place. It's basically like the energy that they need to hit each other with to get up and over basically the hill to the other side. And we talked about sort of two different types of energy diagrams that go with two different types of reactions. And here, draw it here perhaps, a reminder that we have one that looks something like this. And if this is your reactants, this is your products, this is energy, and our reaction is progressing in this direction. This is a exothermic reaction diagram. We know it's exothermic, and it means that heat and energy is released or given off. And we know that based on the position of the reactants to the products. Our reactants are higher in energy than our products, which means the only way for them to get down there is they have to release that energy or give off that energy in that case. Here's our activation energy, which is that, again, that hill that those reactants have to climb to get to the other side. When you do get to the top, as we see in that previous picture, and we talk here, at the very top of the hill, this is what is, again, sometimes referred to as the transition state. The transition state, pretty much in a reaction, is the highest point in a chemical reaction. It is pretty much, as we can see in this picture here, it is where we have that, what is sometimes referred to as a transition state complex, or it's sometimes referred to as a activated complex. And as you can see here, this is our guy that has partially made bonds and partially broken bonds. This is quite an intermediate. As you hopefully know in chemistry, right, things in high energy are not particularly stable. Pretty much everything that we do in chemistry is to get things to a better state of energy, a lower state of energy. So things in really high energy like this intermediate here is really unstable, and it doesn't stick around for a very, very long time. It will, relatively quickly kind of drop down the hill to the other side. A lot of times in reactions, it's very hard, for example, to try to isolate that intermediate because it's so high in energy. It doesn't hang around a long time. It just kind of quickly converts itself to products. And again, really, that's the point of a lot of what we do, as I mentioned, is to sort of lower everybody's sort of energy to a much better stable part. We also had a endothermic sort of diagram that we saw here, energy in our reaction proceeding in this direction here. And this one will look something like this. This is our reactants, this is our products. In this particular case, that is our activation energy. Our reactants are actually lower in energy than our products, and that is what tells us it's an endothermic reaction. And that is when heat and energy is absorbed. So again, in order for our reactants sort of get up to the products, we actually have to put energy in to this reaction to do that. Now, a couple other things we talked about in sort of that earlier chapter as well with energy is we know that if you take the difference here, right, between the reactants and the products in energy, that is your delta H of your reaction. That is your change in enthalpy. And remember, to calculate something like the delta H of a reaction, we basically take the delta H of our products, which is our final state, minus the delta H of our reactants, which is our initial state. Remember, it is a state function, which means it doesn't matter how you get there. The only two things that are important is where you started and where you ended. So I think we saw a picture of like some hikers that went up a mountain in terms of their potential energy. So if we were to calculate our delta H for the exothermic reaction, our products are lower in energy, so that's going to be a smaller number, minus our reactants, that's higher in energy, which is a larger number. That's going to yield us a negative value for delta H. And again, a reminder that if you do see a delta H for any type of reaction and it's negative, the number really doesn't matter. The negative sign is actually important. It will tell you that this reaction is exothermic overall, energy is being released. Same thing over here. If we look at the difference in the energy of our reactants to our products, that would be our delta H for this reaction. And in this particular case, it is different. Our delta H of our products is actually a larger number than our reactants, which is a smaller number. That is going to yield you typically for a endothermic reaction a delta H value that is positive. As you might remember, in most cases, if you're doing something with energy, if you end up with a negative value for energy, that usually implies some type of exothermic process. Energy is being released, it's happening. And if you basically for energy end up with kind of a positive number, that usually implies that a endothermic or energy is being absorbed is happening in this particular case. Any questions on that there? A little review, I think, of chapter 10. I think we already saw that. Now, a reminder that we're sort of talking about the rates here of reaction, and the one main thing that sort of determines how fast or how slow a reaction takes place is actually that activation energy. It is, as you can see here, really the hill that those reactants has to climb to get to the other side. That means if you have a small activation energy, you probably will have a pretty good rate happening because it's not going to take a lot of energy for those reactant molecules to get to the other side. If you have a larger activation energy, your rate probably will be a little bit slower, and that's because there's going to be less amount of reactant molecules that have enough energy to get to the other side. One of the ways that you can increase the rate of a reaction is to, for example, add a catalyst to a reaction. And a reminder that a catalyst is not a reactant, it is not a product, and it does not get used up in the reaction. Now, a lot of times you will find catalysts in a chemical equation written on the arrow, something like a metal like platinum. Sometimes they may just write H plus, which means it's an acid being used as a catalyst. So a lot of times catalysts are basically written on the arrow. What a catalyst does, because it's not really a reactant, not a product, and it really doesn't get used up in the reaction, as we might have addressed before, it does find sort of a, I would put it this way, a more efficient way for this reaction to take place. So a more efficient way for it to do that. Now, that could be something as simple as it's a piece of metal like platinum or something like that. And you put this piece of metal, and what happens, for example, let's just say we had some gas molecules flying around looking to react. These gas molecules would find themselves perhaps attracted to the metal. And what that's then going to do is put these gas molecules now very close to one another and going to sort of facilitate the reaction beginning. It could also help with getting those bonds broken as well, but it's just going to bring everybody into the same proximity. If you try to do this, for example, without the catalyst, what you have is basically two gas molecules, for example, flying around, and you got to wait until, they kind of find each other as they're flying around to come in contact. So a lot of times a catalyst just provides sort of a substance or a platform for that reaction to occur a lot more efficient. Ultimately, what it does in terms of energy is by finding this sort of more efficient pathway for this reaction to occur, it actually will lower the activation energy. So here is the reaction with a catalyst. This is our non-catalyzed reaction. And you can see that with the catalyst, it lowers the activation energy. So what is that really going to do? What that's going to really do is it's going to allow all of these reactant molecules now to go, cool, I just need to go this high. I don't have to climb as high to get to the other side. And you're going to have a lot more reactant molecules going to be able to get there, as opposed to in the uncatalyzed reaction, they got to climb this hill basically to get to the other side, which is obviously much, much higher. So it's like if you had to climb a giant hill to get to the other side of campus versus if you just had to go up and over like a speed bump, right? A lot more people go up and over the speed bump than a giant hill that you have to walk. So it takes a lot less energy as well to do that, right? As opposed to go over a giant hill to get to the other side, say, of campus or something like that. So by finding this alternative pathway, it lowers the activation energy. That gives more reactant molecules the opportunity to get up and over to the other side to make products. The end result of that is you will see, obviously, in most cases, your reaction will speed up. I would say 99.9 times or even more, when somebody talks about a catalyst, this is sort of what they're talking about, which is the idea of speeding up a chemical reaction. There are actually catalysts which are not talked about a lot, which are referred to as negative catalysts, and they actually slow down a reaction. So they actually have some catalysts that can slow down a reaction. But I would say in most cases, if somebody's referring to a catalyst, they're usually talking about in the aspect of speeding up the chemical reaction. Any questions on that there? So let's talk then a little bit about equilibrium, which is the other main part of this chapter. And equilibrium is an important topic, which I mentioned you will see again in 1B. Frankly, that is most of what you'll talk about when you get to 1B is all about equilibrium, every equilibrium you never probably want to know about. But equilibrium does involve a specific type of reaction, and the type of reaction that equilibrium basically involves is this type of reaction that basically has arrows heading in both directions. So very similar to what we saw when we looked at weak electrolytes. This is what is sometimes referred to as a reversible reaction. And a reversible reaction really has two directions. And the forward direction is this direction here, where we go from reactants to products. This is the forward direction. But in these type of reactions, which are reversible, at some point you will actually create enough products that the products will decide, hey, we would like to react with each other and actually go back in the other direction. So what happens is as you build up the products, those products will eventually be enough there for them to actually start to react. And this is what is known as a reverse direction. And that's basically when your products come together to go backwards and make your reactants. This will continue until chemical equilibrium is reached. Now, people have a very much misunderstanding about the word equilibrium here. And it's probably because the word sounds like equal. So when they hear equilibrium, most people think, oh, that must mean we have the same amount of things on both sides of the arrow. And that's really not the case. So when something reaches chemical equilibrium, we're actually talking about the rate, like we were just talking about a second ago. And what we're talking about is the rate of the forward direction of that reaction will eventually equal the rate of the reverse direction. So that is what is meant by equal, and that is what is actually equal, is not the amount of concentration we have on both sides, but it's actually the rate. So just as fast as the reactants make products, those products will recombine and go back the other way and make reactants. So it's going back and forth, the forward direction and the reverse direction at the same rate. So what does that do to everybody's concentrations or even pressures? What it does is it essentially will lock everybody into place in terms of their concentration as to where they were at when it reached equilibrium. And they basically will not change. You could also lock in their pressures as well if you're dealing with gases and you look at pressures rather than concentrations. So when you reach equilibrium, it basically will lock everybody into place. So for example, if I had this reaction, and let's just say initially I had like 2 molar of this guy and 4 molar of this guy, and I had nothing of product. So I'm just starting with all reactants initially. And when this thing actually reaches equilibrium, I'll call that E there. When that reaches equilibrium, maybe I got, 1 molar of this guy left, maybe I got 2 molar of this, maybe I made 3 molar of this guy, and maybe I made 2 molar of this guy. So they're not all equal in terms of their concentration at this point. But what it means is if this has reached equilibrium, these concentrations will basically be locked into place. They will basically never change unless you do something to screw up the equilibrium. Yeah, and we'll talk about how you can screw up the equilibrium later on in this chapter. But basically, this will continue to occur, and it will continue to be at equilibrium. Any questions on that there? So when we reach equilibrium, forward reaction, reverse reaction, the rates of those are the same, locks everybody into place. By the way, like I mentioned before, if we were dealing with pressures, these could all be like atmospheres, and everybody's pressures at equilibrium would also be locked into place. Now, one of the ways that you can see equilibrium, or one of the places where we actually do see equilibrium, is actually when we see phase changes. So it can be chemical reactions that occur, but it can also be physical processes where we actually see equilibrium occur. For example, if you took water in its solid form, which is ice, and it will be in equilibrium with its liquid form at what is known as its normal melting point or freezing point, and for water, that is 0 degrees Celsius. So at exactly 0 degrees Celsius, you have both of those states in equilibrium with each other, and we are not changing the temperature at that point. So you basically have, at exactly 0 degrees, it'll be like that plateau line we saw, I think, in chapter 14, right about there between our solid and our liquid. You will basically have like ice crystals happening at this point. You'll have a little bit of solid there, you'll have a little bit of liquid there. And as again, not to, for example, you get above 0 degrees that you actually transition into ice or liquid water, I'm sorry, and not till you get below 0 degrees that you transition into ice, right? And that was our heat of fusion to do that transition that we talked about to go from solid to liquid or liquid to back to solid. Same thing happens when you reach the boiling point for water, right? And that is liquid going to gas, basically, or steam. And that happens at the normal boiling point for water, which is 100 degrees Celsius. And again, exactly at 100 degrees Celsius, you have basically both phases happening at the same time. You have some liquid water, you got some steam happening. This is what's happening at the surface, really, of any liquid. You got some guys jumping out of the liquid phase into the gas, and you have some slower moving gas molecules dropping back into the liquid. So you're at equilibrium. Not until you get above 100 degrees Celsius did you really kind of fully transition into the gas phase, for example, for water, and not until you get below 100 degrees that you transition into the liquid phase here for water. So even in physical processes, we do have equilibrium that occurs. And again, at that temperature, we got the forward reaction, reverse reaction sort of happening at the same rate. Now, when we look at a beaker that is reaching equilibrium, and maybe we mix together something like iron 3 and a little thiocyanate action, like maybe it did in a lab, making this dark blood red complex ion type deal here. Kind of a dark red. And it got red. I'll put it in my beaker as well. So you mix these together and boom, you hit a red beaker. And this reaction basically has reached equilibrium. And when you look at the beaker, it doesn't look like much is happening because, hey, it turned red and it doesn't look like it's changing or anything like that. So on the macroscopic level, the big level, it may appear to you that nothing is happening. This reaction is like over, it's turned red, it's done, and stuff like that. But if you were to be able to super zoom in on your beaker, there is a lot of frantic activity of these guys combining to make this complex ion, and a lot of those guys coming back both ways. So there is constant forward direction and reverse direction happening in this reaction, even though on the big level, when you look at it in your flask, beaker, whatever it may be, it appears to you that nothing much is happening, it's over. But there is a lot of frantic activity sort of happening kind of below the surface in this case. And again, that's what is meant by equilibrium, is static macroscopically, but microscopically, there's a lot of activity that's occurring. One of the interesting things about these type of reactions are you basically can screw up this type of reaction and do something to it that will mess up the equilibrium. But this type of reaction will always try to get itself back into equilibrium. So it can actually self-correct itself and get itself back to an equilibrium position, even if you did something to it that kind of messed it up for a short period of time. And that's what we see here. Again, starting out, in this case, we had all reactants. As the reaction progresses, it eventually reaches equilibrium. And again, at that point, it's going to lock everybody into place in terms of their concentrations. How do you know that when you look at a graph or something like that? Well, what we see here is the rate of the forward direction in a lot of cases will predominate at the beginning if you're starting with just reactants. That means at some point you'll get enough of those products, as I mentioned, that the products will start reacting. And they basically will both level out and equal each other, the rate of the forward direction and the reverse direction. And that is where chemical equilibrium has been reached. So for example, if we looked at this reaction here of a little ammonia formation, I'll balance it like I'm in chemistry class or something. I do that there. That looks good. So if we were to look at sort of the progression of the reaction and really the concentration of our reactants, you know, we would have some N2, we would have some H2, and this is kind of time as well. And we would have pretty much none of our products here. So remember that if we only started with reactants, the only option for this reaction to happen is because we're only starting with reactants, that forward direction is really our only option at this point. We have no products to react to go the opposite way. So in this case, it's all got to be forward direction. Now, in order to make products, we need to see our reactants starting to decrease with time because they have to make the products. At the same time, we will start to see our products starting to increase with time. And again, like I said, eventually they will kind of level out a little bit. And what will happen is, if I could draw some straight lines, you can pretend they're straightish lines. That was definitely not so straight there. We'll assume that my straight line started right about there. And basically, when we do hit straight lines, basically for all these, they basically all plateaued out. And basically what that means is each of these concentrations, if they were straight lines, were basically going to be the same and it continue to be the same. And when that happens, that is when chemical equilibrium has been met in this particular case. Any questions on that there? Now, concentrations, again, when they reach those levels and that rate of the forward direction equals the rate of the reverse direction, that is when we meet that chemical equilibrium. So let's just say, for example, we have this reaction here, which is actually at equilibrium. And we decide that in this case, we actually want to add some more water to this equilibrium. And if we were to add more water, take a moment and think about how does the concentration of everyone change? Does it increase? Does it decrease? Does it stay the same? So take a moment, think about adding water where water is, what's going to happen, what you think is going to happen when you add that water, and how that's going to affect everybody's concentrations. All right, so let's take a look. So in this case, this system is at equilibrium. So at this point, basically the rate of the forward direction here will equal the rate of the reverse direction. So really we got a little bit of some products, we got some reactants going on at this point. So we decide to add more H2O, which in this case is over here on our reactant side. So what that's going to do is, in this case, will that cause the forward direction to occur, or will that cause the reverse direction to occur? What do you think? Which direction will this reaction occur now? It's a 50-50 shot. What do you think? It's going to occur in the forward direction here, yeah? And that is because we basically just added more reactants, right? And because we added more reactants, those reactants are going to be able to find each other a lot easier. And that is going to kick off the forward direction in this case. And because that's going to kick off the forward direction in this reaction, that means we're actually going to make more products at this point. and we would expect the concentration of H2 to increase. We would also expect the concentration of CO2 to increase as well, because again, that forward direction, this reaction is going to predominate, and that's going to dump out some products. Now remember, it's still a reaction, which means the only way we can make products is we have to use up reactants. So in terms of the CO, we would expect the concentration to go down, because the CO and the H2O have to come together to make our products, right? Now, in terms of the H2O, what you will pretty much overall see is it will go down. But what you actually might see is, for the water, you might actually see it go up first, and that's only because you added it. So that's why you're going to see a really big jump in it. But as soon as it starts reacting with the CO in this case, you then should see it start to come back down, its concentration. It may actually, in some cases, end up being higher than it started with, and that's only because you added it. So that's kind of an artificial high. But ultimately, it should also be coming back down as it's reacting with the CO to make our products. Any questions on that one there? All right, so same idea. What's going to happen to everybody's concentration if we add H2 in this case? So take a moment and think about what will happen here. So we're basically increasing our products. So by increasing our products, what that's going to do is now make actually the products more available than reactants. And that's actually going to kick off the reverse direction of this reaction to occur. Again, you have more products than you do reactants. So it's actually going to head from products back to reactants in this case. The result of that is, in this case, you're actually going to be making more reactants because it's heading in that direction. And we would expect to see the water's concentration increase, also the CO's concentration increase. Once again, the CO2 is needed to react with the H2 to make those reactants. And we will see a similar effect on the H2 than we did with the water. Again, it will probably go up high because you added it. But once it starts reacting with the CO2, you should start to see its concentration actually come back down as well. Any questions on that there? So again, when we talk about these reversible reactions and we talk about these sort of reactions and doing something to these reactions, what you really want to kind of think about is, whatever you're doing, will that cause the forward direction to occur, or will that cause perhaps the reverse direction to occur? And then you could kind of figure out, just logically thinking, if the forward direction occurs, you should be making more products. If the reverse direction is occurring, you actually should be making more reactants. So you can kind of determine what's going on with that. Any questions on that there? All right, so let's take a look at some of these things here. One of the relationships that we see with equilibrium is a really important relationship, and that is capital K. And capital K is the equilibrium constant. And the equilibrium constant is a constant value, and it's not to be confused with, dramatically drawn here, a small k. Small k is actually the rate constant, which deals with kinetics. So it's actually important in chemistry, if you're talking about equilibrium constant, that you do make it a capital K, because if you use a small k, it actually means something different in this case. The equilibrium constant is constant. It is constant for the reaction as it's written. So what's on the reactant side, what's on the product side. It is also a constant value at a specific temperature. And actually, as we will talk about, temperature is the only thing that will affect the actual value of the rate constant. So if you keep the temperature constant and you run a reaction a bunch of times, you should get the exact same value for K for every reaction that you run, as long as you keep that temperature constant. So that is, again, the only thing that can affect it. How do we calculate the K? Well, once again, as I mentioned earlier, When you see these brackets, that again is concentration. And that is, once again, molarity is pretty much what we're talking about. So K is really calculated as the concentration of your products divided by the concentration of your reactants. So we also take into account the coefficients in the balanced equation. So we take our products, the concentration of C to the C, the coefficient, concentration of D to its coefficient, divided by the concentration of A to its coefficient, and B to its coefficient. And when you do this with concentrations, this is sometimes referred to as the Kc value. C meaning concentration. You basically did it with concentration. And in this case, the Kc would be our products over reactants. The K is actually one of the few things in chemistry that actually is just a number, no units attached to it. So the equilibrium constant value is actually just a number. And that number does tell you something. It tells you that when you reach equilibrium, what you should expect to sort of mainly be there. So what I mean by that, if you have a large value for K, what that means is in order to get a large value, mathematically speaking, the top number here needs to be a large number. Bottom number needs to be a small number to get a large value for K. And if you do that, that means that when you reach equilibrium, you will mainly have products present. Or you have more products than reactants present. If you have a small value of K, that means in order to get a small value of K, you actually will need a larger number on the bottom and a smaller number up on top. And that would mean that you would mainly have reactants at equilibrium. So what is considered sort of a large value or a small value? Well, it is that large number of 1. Yeah. So 1 is considered a large value of K. So anything 1 and above is considered to be a big value of K or a large value. Anything less than 1, if you got like a negative exponent, like times 10 to the minus 3 or something like that, is a small value of K. There is extremes to that. So there are K values that are, for example, like times 10 to the 54, which is a super large number. There are K values that are extremely, extremely small, like times 10 to the minus 34, which is a super, super small number. And there's K values anywhere in between those numbers as well. So there is sort of extremes with anything here, but you can look at the value of K and basically determine, should you expect mainly products when this reaction is at equilibrium or reactants basically being there? If you have a K value near 1, you got probably equal amounts, right? Because the only way to get to 1 is top number and bottom number pretty much needs to be the same number, right? So you'll have kind of like almost equal amounts at that particular case. So here's one way that we can write our equilibrium expression. So again, we're going to take basically our products divided by our reactants. And that's what we see here. So our products is the concentration of NH3. Coefficient is 2, so we got to make sure we square it. Here, our N2, and the coefficient really is 1. And much like everything in chemistry, we really don't put 1 in things. So if there's no number there, it's assumed to be 1. And here's our H2, which is a coefficient of 3. And we would cube it at that point. This, again, like I said before, is done in concentration. This is typically done in molarity. And again, this is sometimes referred to as the Kc value in this particular case. You do need, if you wanted to solve for the value of K, you do need the actual equilibrium concentrations. And those has to be equilibrium concentrations that go into this expression. You cannot use like initial concentrations. You actually have to figure out what the equilibrium concentrations are and put it into here. Now, I mentioned earlier that most of the time, or a lot of the time, we do equilibrium with concentrations and molarity. But in a situation like what we have here, where they are all gases, we oftentimes, when we think of gases, we think of pressure as sort of the thing that we look at. And the standard unit for pressure is atmospheres. So you could actually, if you knew the pressure of each of these gases, you could actually do the exact same type of expression, except using pressure. So you could write something like the K would equal the partial pressure of NH3, and we would still need to square it, divided by the partial pressure of N2 times the partial pressure of H2, also needs to be cubed. And you would do that with everybody in atmospheres. If you have the pressures given to you, it works the exact same way. It's still products over reactants. As you might imagine, since we didn't use concentration on this one, but we used pressures, this is surprisingly, or not surprisingly, this is what is known as a Kp value, which is the equilibrium constant for pressure, basically is what the P is. And again, you may not realize it, but we've already seen an equilibrium reaction and constant. That was when we looked at water in the last chapter, or yeah, the last chapter there, where we had our H plus and our OH minus, right? That Kw is the equilibrium constant for water, that 1 times 10 to the minus 14 number. So this is also an equilibrium expression, and it equals 1 times 10 to the minus 14. And that is our products over our reactants. As we will talk about shortly, there are a couple of things that we actually do not include in the equilibrium expression, and liquids are one of the things that are not included. So when you write a K expression, we include things that are in the aqueous state and things that are gases. So those are the two things that we put in there. The things that we do not include are things that are solid and things that are liquid. And that is why when we write our Kw expression, we don't include the water here, again, because it's a pure liquid in this case. So things aqueous or gases are involved in the equilibrium. And if you just think about it logically, they're involved because they're aqueous, and where we find things that are aqueous are ions. And we have ions floating around, which means they're good to go to start reacting, right? And they can react. Gases are constantly flying around, which means they are also good to go to start to react. Solids, if you think about it, are kind of like if you threw a rock into a beaker, it's just going to kind of sit there on the bottom and not do much, right? And the only way for like a solid to react is it actually has to dissolve. And when it dissolves, it's now no longer a solid, it's aqueous ions. So that's why we use our aqueous ions here, that they react and stuff like that. And liquids like water, their concentrations are fairly constant over the whole process. It doesn't change very much. There's just tons and tons of water molecules. So its concentration really doesn't change or affected as time goes on. So when we write these K values, as you can see here, just from this one slide, there's Kc, Kp, Kw. When you take 1B, like I said, the class is brought to you by the letter K. You'll learn every single K with every little subscript on the bottom, Ka, Kb, Ksp, Kf. It just keeps going. And it's pretty much everything that you'll learn about in that class. Any questions on that there? Now, K, as I mentioned before, is always the same value as long as the temperature doesn't change. And that is a really important aspect of K. That's why it's called the equilibrium constant. It will not change. The reaction, as long as you don't change the temperature, can have many positions. So what does that mean? So for example, let's say we have this reaction of the A plus the B goes to C plus the D, right? And let's just say we did one experiment where we had just reactants and we didn't have any products. Then we did experiment 2, where we maybe had no reactants, but we did all products. Then maybe we did experiment 3, and maybe we had some reactants, we had some products to begin with. If you did all three of these experiments at 25 degrees Celsius and you calculated the K value for each of those at 25 degrees Celsius, they all should be the same. And sometimes people don't understand that. They go, wait, in this experiment, I use like twice as much as I did in the first one, or I use all products in this one and reactants in this one. How can they all get to the same K value? And the simple explanation is this. For example, let's say you wanted for this reaction the K value to be 2. There are many ways I could get to 2. I could get K is equal to 4 divided by 2 equals 2. I could get to K is equal to 8 divided by 4. That equals 2. I could get to K is 2 divided by 1. That equals 2. Those are all different numbers, but the ratio of products to reactants all end up being the same number. And that's what happens here in these equilibrium reactions, regardless of how much you start with in any experiment. As long as you keep that temperature constant, they will always come to rest at equilibrium with the same proportion of products to reactants, the same ratio basically, and that is why it is the same value there. So even though, again, you start with different amounts, it will always come to rest the same thing. Now, for example, if you did these exact 3 experiments, exact same way, but you did it at 35 degrees Celsius rather than 25 degrees Celsius, all 3 of those experiments at 35 degrees Celsius, the K value will be the same. But if you compare the K value at 25 degrees to the K value for those experiments at 35 degrees, they will be different values. So that is what we're talking about when we talk about the K value will be different at different temperatures. The K value at this temperature will be different than the K value at another temperature. But if you're running a bunch of experiments at a high temperature, a low temperature, and you keep the temperature the same for all those experiments, the K value should be the same. But upon comparison between different temperatures, you will have different values of K. That is why, technically speaking, when we talked about Kw equaling 1 times 10 to the minus 14, it is technically for 25 degrees Celsius. Now, if you technically were doing some type of experiment that wasn't 25 degrees Celsius and you need to use Kw, technically speaking, it would have a different K value at a different temperature. Any questions on that there? All right, so let's take a look at this one here. We want to determine the equilibrium expression. Once again, we're going to go with our K is equal to our concentration of our products divided by the concentration of our reactants. So in this case, our product side, we have H+, we have acetate, divided by our reactants, which is a little acetic acid here, I think. And that looks like the one box there, which should be A. Again, products over reactants, not the opposite way around, right? So not like that guy. All right, so let's take a look at this one here. For the reaction below, we want to calculate the equilibrium constant for this reaction. These are our equilibrium concentrations that's given to us. So as I mentioned before, in order to actually calculate the value of K, you do need the equilibrium concentrations either given to you, or you may have to calculate them in some cases. And the first place we want to start with is our equilibrium expression. So we're going to go our products, which is our NO2. We do need to square it because of the coefficient that is present. That's going to be divided by our N2O4. Again, the coefficient here is basically 1, which means we don't need to do anything to it. So putting in our equilibrium concentration is going to give us 0.06. Again, we're going to square it. Divided by 0.055. And we'll go with it here, just make sure they're right, hopefully. Going to give us a 0.065, which hopefully should be the one they circled, which is good. A reminder that the K value does not have units associated with it. So that would be your answer. You could write in scientific notation if you wanted to. Here we got 2 sig figs on everybody, so 2 sig figs for the answer. That is considered a small value of K, as it's less than 1. That means that when we would reach equilibrium, we would expect to have mainly reactants present. Again, because of the small value of K. Any questions on that one there? All right. So for each of these here, we could write our equilibrium expressions. So as we saw earlier, that again would be our NH3, and we would square it, divided by our N2 and our H2, that would be cubed. And again, that would be our Kc for this one, as we just did earlier as well. We could write a Kp value, which again would be the exact same thing, just with pressures, and they would need to be in atmospheres. Here we would go with our K here, and there would be our Kc, concentration of H plus, Cn minus, divided by our reactants, HCN. In this case, we cannot write a Kp because there is no gases, right? So there's no gases present, which means you have no pressure. So you got no pressure, you can't write a Kp. So in order to write a Kp, it really has to be some type of reaction that has gases present. And again, if there is no gases, then you obviously can't write it. Any question on those there? So, as I also mentioned a second ago, the two things that we really do not include in our equilibrium are solids and liquids, not included. This is what is sometimes referred to as a heterogeneous equilibrium. It just means that everybody's in this different phases. This is homogeneous equilibrium, where everybody's in the same phase, like homogeneous mixtures, everything looks the same throughout. Heterogeneous mixture, you see different layers. So here we have different phases happening. Here we would write our equilibrium expression. The K here would be the concentration of O2. We would cube it. And by the way, that is a solid, so not included. And our reactant side is also a solid, so we would not include it. So that would actually be our Kc expression for this guy. By the way, since there is a gas, you actually could write a Kp, which would be the partial pressure cubed of O2 in this particular case. So coming here on the bottom one, this is basically our decomposition of water. So we could write a Kc is equal to our H2. Again, we need to square it. And our O2 in this case, again, coefficient of 1. We do not need to write it. Another one that we could write a Kp, and it would just be the partial pressure of hydrogen times squared times the partial pressure of oxygen, and that would be a Kp type of value and expression. Now, it is possible, for example, if you had something like this, maybe, I don't know, maybe you have a solid actually on the product side, and you do have stuff on the reactant side that you want to include in your equilibrium expression. To do this, since the product side would not be included, we actually just do 1 over the reactants in this case. So if you had something where nothing on the product side would be included, you basically just do 1 over your reactants. Any questions